Shalom. Good morning, ladies and gentlemen, dear valuable or valued student. I'm very happy to be with you or in front of you this morning or this afternoon, depending on what time you're watching this video. As promised, we are going to tackle a Gaussian quadrature formula. What is Gaussian quadrature formula and why do we need this formula? As you know, in mathematics, we always want to improve the accuracy of methods, or sometimes you want to maximize or minimize or optimize optimization. You have few resources, you want to use few resources to achieve something great with few resources. So let me compare first of all the previous methods and show you some of the drawbacks and why we need more advanced method. If you recall, with the Newton-Cotes method, we saw that with Newton-Cotes method, I will take the example of the three methods, in total 4, because we have the trapezoidal rule, we have the 2 Simpson rule, that is Simpson, and the 3/8 Simpson rule, that's already 3, and we have the Boole's rule. These are the 4 rules that we tackled in the previous sections. Okay, now let us look at each of them and evaluate their degree of precision compared to the number of node points used to achieve the results. In the case of trapezoidal rule, we all know that trapezoidal rule's degree of freedom is, degree of precision is 1. And how many quadrature nodes do we have in the trapezoidal rule? 2, x0 and x1. But with 2 points, we achieve only 1 degree of precision. Okay. So if we move to the next Newton-Cotes formula is the Simpson rule. Simpson rule, degree of precision is 3 for both Simpson and the 3/8 rule. There, the degree of precision is 3. But for Simpson's rule, we use 3 polynomial evaluation. That is f sub 0, f sub 1, and f sub 2 for Simpson rule. And for the 3/8 rule, we use 4. F sub 0, f sub 1, f sub 2, f sub 3, f sub 3. That will be 4. All right. But the degree of precision is 3. So you see that the number of points that we are using is greater than or equal to the degree of precision. Okay, now if you look at the other case, the Boole's rule. In Boole's rule, we use 5 polynomial evaluation, and the degree of precision is also 5. You see that the number of points is 5 and the degree of precision is 5. So the n, which is the degree of precision, is equal to the number of polynomial evaluation. But in others, the number of polynomial evaluation is greater than the degree of precision, like in the case of the trapezoidal rule, where the degree of precision is 1, but we use 2 points. So the number of points is greater than the degree of precision, which is 1. And for the Simpson rule, the degree of precision and the number of polynomial evaluation are the same. But for the 3/8 Simpson rule, the number of polynomial evaluation is 4, whereas the degree of precision is 3. So number of points greater than or equal. So we use more points for less degree of precision. Similarly, for the Boole's rule, degree of precision is equal to the number of points. So meaning that to achieve a particular degree of precision, the number of points should be greater than or equal to that degree of precision, which is a lot. Okay, now in the case of Gauss quadrature formula, what we want to use less point but achieve a higher degree of precision. So that is it. And that's the beauty of the method, as you are going to discover very soon. And I plead with you to be ready to swallow and digest the beauty of what we are going to do now. Gaussian quadrature formula. So, an capital N point Gaussian quadrature rule is a rule that is designed to yield an exact result for polynomial of degree less than or equal to 2 capital N minus 1. So you can see that the degree of precision here, 2 capital N minus 1, is far much larger than capital N. So you see, we use less point, capital N, but we achieve a degree of precision of 2 capital N minus 1. So almost the double. But how do we achieve this? The following theorem gives us the methodology. So first of all, we need to define a polynomial Q of degree n plus 1. Or if you want, we can even take this n, the result will yield the same thing. Right? If we are using n plus 1 because of the interpolating polynomial, because if you recall, anyway, not exactly. But what I want to say here is that our Gaussian rule, if you look at the formula here, if you look at the cursor is around the rule. So if you look at this rule, you will see that in this rule we are using n plus 1 polynomial evaluation, n plus 1. So that's why the degree of the polynomial Q is also n plus 1. Because to achieve this degree of precision, we need to obtain optimal positions of our x. That is the nodal point or the quadrature nodes, x0, x1 up to xn. Right? It's because in our formula we started from 0 to n, so meaning that a total of n plus 1 point. That is why we are using a polynomial of degree n plus 1. Otherwise, if we use irony from 1 to n, meaning n point, we could have decided also to use a polynomial of degree n. So that's why I was saying that this can be adjusted depending on the notations. Right? We can use polynomial of degree n, and in that case we need n point instead of n plus 1, and the summation also here will be from 1 to n. And if that is the case, then the degree of precision will be 2n minus 1. So capital N here, capital N is used in such a way that if your degree or the degree of your polynomial is whatsoever, then that will be your capital N. Right? Capital N in this case is n plus 1, which is the degree of the polynomial that we use, right, in this theorem, and whose roots are what we want, because the roots of this polynomial will be the optimal position of the quadrature nodes to achieve this optimal degree of precision. So this condition is imposed in order to define the coefficient of a polynomial of that degree. If you have a polynomial of degree n plus 1, by using such an integral, it will give us a system of equation that will allow us to determine the coefficient. Okay, so in this quadrature formula, you can see that our wi, the weights, are also similar to the weights when we apply Newton Cotes method. It's similar. It is similar. Okay. The quadrature formula that arise as application of this theorem are called Gaussian or Gauss-Legendre quadrature formula. So in order to exemplify, to understand the theorem, we need to apply it to a particular example. And for that, we use a 3-point Gaussian rule or quadrature formula. And for that, we will use the interval -1, 1 to perform this computation. So let us find our quadrature formula, which means that it will be a sum I running from 0 to 2, because I is 0, 1, 2, a total of 3 points. And then we determine the wi's and the xi's. And we saw that the xi's, that is the node points, are the zeros of Q. So for that, we need to find Q. Right? The Q here is like Legendre polynomial. Right? So we write the general formula for a polynomial of degree 3, because we want 3 points, right? Because we say 3 points. If you say 3 points or 3 nodes, it means that the degree of the polynomial will be 3. A polynomial of degree 3 with 3 roots. So we write the general formula, which is this the general formula for a polynomial of degree 3. And we impose the condition of the theorem, the integral from a to b of x to the k qx dx equal to 0 for k running from 0 to n, that is 0, 1, 2 in our case. So this is what we obtain. So this will give us a system of equations, 3 equations in 4 unknowns. So it's overdetermined. We have to make some choices. So if we choose a0 equal to a2 equal to 0, our q will reduce to this expression, and then integrating the second integral, that is x times qx dx from -1 to 1 equal to 0, we obtain a simple equation. And if we choose a1 equal to -3 and a3 equal to 5, from that, because that's the relationship that this system will give us, for a choice of a1, you get a3. So we obtain this q, and we find the root. So we solve qx equal to 0 and find the root. So qx equal to 0, we can see that x is a factor. We can factor by x, and then we solve the equation. So this is equal to 0. So please correct it. Then these are the 3 roots: minus square root of 3 by 5, 0, and square root of 3 by 5. So these are the 3 roots. So these are our x0, x1, x2. Now we need the w's, and for the w's, you can integrate directly the cardinal function if you want, or you can use a method, which is the one that we are using here, which is called the method of undetermined coefficient. So the method of undetermined coefficient, in the method of undetermined coefficient, we use the fact that our Gaussian quadrature formula or quadrature rule is exact for polynomial of degree less than or equal to 2 capital N minus 1, or in this case 2n plus 1, where n is equal to 2. So 2n plus 1 will be 5, polynomial less than or equal to 5. But we don't need to use all the xk for k running from 0 to 5, because we only have 1, 2, 3 unknown. So we can use 3 different values of k. That is k equal to 0, equal to 1, equal to 2. So polynomial degree less than or equal to 2. And this is exactly what we have here. We want to write that this formula is exact for x equal to 1 for 1x and x squared. So we impose that and we solve. We obtain the set of three equation 3 unknown. So meaning that we get unique value of W0, W1, and W2. So this is a system that we obtain by integrating dx, right? Where f of x each time is 1 for this first case. The second time f of x is x. For the last case, f of x is x squared. So you substitute here. So if you say that this rule is exact for this polynomial, it means that in this formula, in this rule, this is the rule, it's approximate here, but exact means that I will write equal here. This approximation sign will be equal for f of x equal to 1x x squared. So if you take, for instance, f of x is equal to 1, I substitute the integral 1 dx, and I'll say is equal to W0 times 1, because f is constant, it will be 1 regardless of the argument. So W sub 0 times 1 plus W sub 1 times 1 plus W sub 2 times 1. So that's what we obtain here. Similarly, if f of x equal to x, meaning that f of x will take the value of the argument, f of x is x means that whatever the argument is the result. So I integrate x from -1 to 1, the result is 0, which is here on the left, equal, now the right hand side is W0 times f of x at this point. But since f of x is x, it means that f of x will be negative square root of 3 by 5 for this position, and that's exactly what we have here, times W0, and then f of 0, which is 0, times W0, since f of 0 is 0, times W1, that expression will cancel out, that's why it's not present here. Now for the next one here, since f of x is x, then f of square root of 3 by 5 will be square root of 3 by 5, that will multiply W2, and that's exactly what we have here. So similarly, if you take x squared, f of x equal to x squared, you integrate x squared from -1 to 1, you obtain 2/3, and now the right hand side, which is the rule, will be W0 times f of negative square root of 3 by 5. So since f of x is x squared, so it will be the square of this quantity. If you square negative square root of 3 by 5, then the result will be 3 by 5. And that's exactly what we have here, 3 by 5 times W0. So similarly, f of x is x squared. So if x is 0, 0 squared is 0. So 0 will multiply W1, and therefore W1 will not be present. Now, f of x equal to x squared. If x is square root of 3 by 5, and you square square root of 3 by 5, the result will be 3 by 5. So 3 by 5 will multiply W2, and that's exactly what we have here. So we obtain then this system, W0 plus W1 plus W2 equal to 2. So that's what we have here. That is our first equation. And the second equation, we have we can see that we have the same factor here, square root of 3 by 5, square root of 3 by 5. So we can divide the entire equation by 3 by 5. We obtain negative W0 plus W2 equal to 0. So we can multiply both sides by -1. So we obtain W0 minus W2 equal to 0, which is this second equation. And for the last equation, which is this one, we can multiply, because this equation can be written 3 feet W sub 0 plus 3 feet W sub 2 equal to 2/3. So we can multiply the entire equation by 5 to cancel out the denominator. If we multiply by 5, this 2 will be multiplied by 5, becomes 10. Now the 3 in the numerator here, we can divide the entire equation by 3 to cancel out these terms, right? So if we do that, 3 divided by 3 will be 9. So meaning that the right hand side here will be 10 by 9, and because we multiply by 5 and we divide it by 3, the coefficient of W0 and W2 will be 1. So we get this. So solving this, we obtain these values and we substitute that into our rule. And this is our 3-node quadrature, Gauss quadrature formula. Right? And as you can as I mentioned already, this formula will be exact for all polynomials of degree less than or equal to 5. Because n is 2, the number, n is 3, the number of point 1, 2, 3. Three is the number, we say that n was the number of point of evaluation, 1, 2, 3. Yes. Now if you multiply 3 by 2, 6 minus 1, 5. Right? So that's what we have here. Alright. Now for the 2-point quadrature rule, it is similar. You can proceed exactly in a like manner and you get the roots to be these two values, negative, plus or minus 1 by square root of 3. And for the cardinal, for the weights, you can proceed in the same manner by using the method of undetermined coefficient, or you can integrate the cardinal function and you get the same thing. Okay, now the next thing that I would like to mention is the fact that these rules, the 2-point quadrature rule or the 3-point quadrature rule, Gaussian rule, are obtained with the interval negative 1, 1. So what if, and that's the case in most of the application, the interval is not negative 1, 1. What are we going to do? Just use a change of variable. If you use a change of variable, this is what we get. X equal to 2t minus b plus a in parentheses, and with the square bracket, we divide by b minus a. So if you use this change of variable, and then we will write an integral, t in our case will vary from a to b. So t varying from a to b, if you substitute t equal to a here, if you substitute t equal to a, you have 2a minus a, which is a. Now we have a minus b is negative b minus a. Then we cancel b minus a. It gives us negative 1. So you see that when t is a, x is negative 1, which is this lower limit of integration. And now if t is equal to b, you substitute 2b minus b is b minus a. b minus a by b minus a is 1, and it gives you the other limit of integration. Okay, now if you use this change of variable and write your integral from a to b, f of t dt, you want to convert it in terms of x, you just solve for t in this equation, substitute, use a change of variable, and this is what you will get. So if you use this change of variable for the 2-point and 3-point quadrature rule, you get this result. So please try that and make sure that you obtain the result. We might do that during the course of the week, during the tutorial, we will see, but you can try already. Okay, now application. We are going to apply these two rules, particularly the 3-point rule, because that's the most popular. We are going to use this 3-point Gauss quadrature formula or quadrature rule to compute the integral from 1 to 5 of dt by t, and the exact value of this is ln 5, which is approximately given by 1.609438. And the second integral is the integral of exponential of negative t squared dx from 0 to 1. And for that, you can see that our interval is different from negative 1, 1. So for the first one, the interval AB is 1, 5, meaning A is 1, B is 5. So we can use those values into this formula. So if you substitute, let me just check for the first one, for this factor. if A is 1 and B is 5, 5 minus 1 is 4. We have 4 here times 5. You can see it's 20. So it will be 20 by 18. Which we can even simplify because 18 is a factor of 2, right? This is a factor of 2, so that is 2 times 9. And this will be 2 times 10. So if we cancel out, it will be 10 by 9, right? So which is what we have here as a factor. Okay, similarly here, negative b minus a, we saw that b minus a is 4, right? Negative 4 by 2, negative 2. Negative 2 times square root of 3 by 5, that's the negative 2 you have here. And the remaining expression here, b plus a by 2, that will be 6 by 2, 3, which is the term you have here. So similarly, you can substitute in a like manner. This is what you will get. Since you know the function is 1 by t, so if we simplify this, we obtain this second row. And then if you use the same denominator, which is 9, then the numerator will be 10 times the evaluation of f at that point, 16 times f at 3, 10 times f at that point, divided by 9. So since f will be the reciprocal of the argument, we'll just take 1 by this, 1 by 3, 1 by that, and we multiply by the factors. And we obtain this result, which accurate to 6 decimal gives us this result. Now, if you compare this result with the actual value, you can see that our result, we captured 6 and those 2 decimals, 6 and 0. You can see that 6 and 0 are captured here. The next is 9, but here we have 2. So you can see that by evaluating the function just at 3.1, 2, 3 point only, we have something that is second order accurate, because second order means one computations of the integral gives us this. We already have 2 decimals that are captured. Okay, now if we compare this result with the result for Bool's rule for 4 equally spaced subintervals, if we have 4 equally spaced subinterval, 1, 2, 3, 4, 1, 2, 3, 4 subinterval, means that there are 5 points in the interval. So meaning that we have 5 evaluations of the function for this rule, 5 evaluations. But here in this rule, we computed only 3 evaluations. But with 3 evaluations, we captured 2 decimals. But here, with 2 extra evaluations for the Bool's rule, we only capture 1 decimal, this one. But the 0 is not captured. So this is more expensive, but gives us a lower accuracy compared to the 3 points Gaussian rule, which only evaluate the function at 3 points, but give us a more accurate result. Okay, so similarly, we can use the same formula in terms of a and b, and use a equal to 0, b equal to 1. Substitute, you obtain this expression in the formula, and then f of t is exponential of negative t squared, and we compute that, we obtain this result. You can also compare that you can compare this with other the previous method. You will see that this is more accurate. Yeah. So that is the power of this Gauss quadrature formula. Okay, so if you recall what I said concerning the polynomial q of the theorem that we need to determine, because we need its roots. The roots are our quadrature nodes, right? What I want to say is that here we solve, we impose this condition of the theorem, writing the general formula of qx, and we obtain the coefficient, and we solve for the root. So if you look at this polynomial qx, which is 5x cubed minus 3x, remember that we said that we chose this point in an arbitrary way, but I also mentioned that, maybe I didn't mention this time. If I didn't, I'm mentioning now. If different people compute this, they will likely obtain different coefficient. But the good thing is that all the polynomials that we will be computing will be multiples of each other. Multiple, of course, the factor will be a real number factor, not a polynomial, right? So meaning that the roots are exactly the same. Now, if you take this polynomial we computed with the Legendre polynomial, we will see that this polynomial will be 3 times Legendre. And Legendre is also a polynomial that will give us the roots, same roots as this one. But the advantage with the Legendre polynomial is that they generalize all these q's. For a given n, the Legendre polynomial of that corresponding degree will give you the q that you need for this theorem. So there's no need actually in real life application to be computing the q's and their roots. There is a recursion formula that allows us to determine this Legendre polynomial. Sorry, it is 2 times, not 3 times, as I said. Okay, so this is the recursion formula to obtain the Legendre polynomial. You see that if you take, like in the case of our 3 points quadrature formula, meaning that the degree is 3. Now, if you substitute 3 here in this formula, you will see that what you will obtain. Okay, let us quickly do that. N equal to 3. N equal to 3. Let me quickly write the formula somewhere so that by the time I will change the slide, I will be able to get it right. So if we use another slide, this one. So what we want to do here, we want to compute Q3x. So what is Q3x? So we have n equals to 3, and I substitute this value into the recursion formula. We obtain that Q3x is equal to 2n, which is 2 times 3 minus 1 by n, which is 3, into x q2, because that's n minus 1, x minus n minus 1, which is 3 minus 1 by n again, which is 3, into q n minus 2, that is 3 minus 2, 1. So we know q1, q1x is x. So we need q2 to compute this. But what is q2? Okay, for q2 I also need q0. q0x is 1. So for Q2, if I use the same formula, Q2x is equal 2 times 2 minus 1 by 2 Q1x, oh sorry, x into that let us so we have x into Q1x minus 2 minus 1 by 2 into Q0x. So if we compute this, we obtain, so this is 2 times 2, 4 minus 1, 3 by 2. So here we have 3 by 2x. Q1 is x, so that will be x squared minus 1 by 2 also. Q1 is 1. So this is what we get. You can even factor if you want. But is that necessary? Is it necessary? Let me see. This is 6 minus 1, 5. It will not cancel with this. Okay, it's not that necessary, but if you want, we can see right that this is 1/2 3x squared minus 1 if you want. So it will depend. Okay, now we can substitute back into this. If you call this 1, this is 2, right? So substituting 2 or whatsoever, yeah, 2 to just indicate that Q2. So 2 into 1 will give us, so Q3x is equal, so this already said this is 5 by 3 x into this entire expression. Let us write 3 by 2x squared minus 1 by 2. Right? Okay, the next one minus, so this is 2 by 3. 2 by 3 Q1. Q1 is x, so we have this one. All right, now if we expand this, this gives us okay, so this will be 15 by, okay, so if we expand this 3 will cancel out with this one, right? So we cancel out with this one, so we have 5 by 2x cubed, right? Minus 5 by 6 x minus this one, so I can say 4 by 6 x, which is equal to 5 by 2 x cubed minus, now this will be 9, this will be negative 9 by 6, so that will be negative 3 by 2 x. So yeah, now if this is our Q3, now if you see Q3, which is equal to 5, okay, I can factor by 1/2. If I factor by 1/2, so we can write that this is 1/2, right? 1/2 times q, our previous q. So this is 1/2 5x cubed minus 3x, and if you recall this is exactly 1/2 qx, and that's why previously we said that qx was 2 times the third degree Legendre polynomial. So you see that instead of computing this Q each time, we just identify the degree of the polynomial and we substitute that value of n into the recursion formula and we will get the polynomial. So the good news about this is that they are documented. I think I already mentioned. And even their roots are documented in most of the numerical textbook, meaning that you can just use them in your program. And you can even write a computer program that will do that. Or still, if you want, you can write the package yourself. If if it's not available in the particular software that you are using, you can write the rule yourself. All right, I think we can stop here for today. Thank you so much for your kind attention. I hope you enjoyed the class and you learned something very useful. I encourage you to go through the video many times and try to do the problems. I will also post the tutorial, this week tutorial. You have till Wednesday or Tuesday for the part-timers to go through the tutorial, and during the class, we just go through and prepare you. Thank you for your kind attention. God bless you. Shalom.